Uh, Good afternoon. Welcome to this NPTEL live session of the course Transition Metal Organometallics in Catalysis and Biology. This is the third NPTEL live session, and we will be taking up questions that you may pose to us during the study of this course, and we will answer them as we get them. So, just to recapitulate, we have covered few topics starting with Repi synthesis that primarily involved dealing with utilization of acetylene to functionalize chemical feedstocks. Then we looked at another very interesting reaction, intriguing reaction you may say, that is olefin metathesis, and there we looked at various aspects of olefin metathesis reaction. We have also looked at the history of the development of olefin metathesis reaction, and then followed by that we have also looked into alkyne metathesis. So this is exactly what has been covered till date for the session that I will be covering. So request you to send us your queries so that we would try to answer them as we receive them. My understanding is that there were no pending queries from the past 2 weeks that have been sent to us over mail. Otherwise, I would have gone over those queries till I receive the new ones in today's live session. So please send us your queries. Now, in the meantime, let me just give a prelude to or briefly summarize what we have spoken about in the last few lectures. Like Repi chemistry, which is a birth child of industry, because Repi himself worked at BASF in 1920s when he was trying to find the utility for acetylene, which is a coal-based product for producing chemical feedstock. Olefin metathesis also, one may say, is a birth child of industry likewise, because the first observation of olefin metathesis were made in chemical industry, laboratories of chemical industries like that of DuPont and various other chemical industry is at that point of time. So these two big discoveries were originated in the industry. And with regard to olefin metathesis, what I would like to add is that this olefin metathesis sort of was discovered in and around at the same time when people were studying olefin polymerization in 1950s, and while studying the optimization with regard to transition metal for catalyst development of olefin polymerization, what they noticed that when they were using propylene as a feed gas for producing polypropylene, they were obtaining polymers of ethylene and copolymers of ethylene and propylene, and that was a surprising observation, because there were no ethylene being supplied in the feed gas. And later on it turns out that the ethylene component of the copolymer they were using actually were getting produced because of olefin metathesis, which were happening at that time, and then that got copolymerized to give ethylene propylene copolymer. So it is a very interesting serendipitous discovery, and that led to a big field in the sense that olefin metathesis engulfs about 8 different subclasses of metathesis reaction. Some of them are polymerization, some of them are intermolecular metathesis, which can lead to ring opening or ring closings, cross metathesis, so on and so forth. So the whole field sort of came into being and can be traced to the first observation of observing ethylene propylene copolymer when one was studying polypropylene chemical feed for olefin polyolefin polymerization purpose. So likewise, this also was an interesting development, and we have followed this development chronologically with time, looking at the individual players from the industry as well as from the academia, like Professor Groves, Professor Katz, Professor Chauvin, and Professor Strock, so on and so forth, who came jumped forthright to explain the mechanism as to how this intriguing reaction of cutting and stitching of olefins were occurring, and then with the expansion of the field, the application, the utility of this reaction, olefin metathesis became a big draw, and finally it went on to win Nobel Prize in 2000, I think 5. So that sort of tells how important this reaction is. Well, this was just a brief overview of the reactions that we have covered. If you can give us some queries. So here we have Sudipta Sarkar saying, can you explain the comparison between Grubbs and second generation catalyst in details? Well, the detailed comparison for this is given in the slides as well. So request you to look at the class recordings for this comparison of the detailed first generation and second generation catalyst. However, I would refer to the work which we have covered in the slide by Professor Wolfgang Hermann, who compared the activity of Grubbs first generation catalyst as well as second generation catalyst for acyclic diene metathesis polymerization, ring opening polymerization, ROMP, and there he had established quantitatively the superior activity of Grubbs second generation catalyst over the first generation catalyst, so it was Professor Hermann's work which sort of first drew attention to the fact that the second generation catalyst was better than the first generation catalyst, and this was reported in an Anguchem paper which was also referenced in the lecture. So request you to read the original paper as well as request you to refer to the slides regarding the difference in activity between the first generation and the second generation. And now the second generation catalyst has one of the phosphines replaced by a N-heterocyclic carbene. As a result, the metal center in the second generation catalyst is more electron rich, and that sort of helps in exhibiting better activity with regard to the second generation catalyst. Any other questions? This was referred, this paper, and when the profile, activity profile for the two catalysts was given. So going back to our discussion on olefin polymerization catalyst, what it turns out that the catalytic moiety were metal carbene species which were extremely reactive. Clear to me, can you refer to the other literature for the same? If you have the Anguchem paper, can we get that reference? Where is the PPT? In the lecture it was not clear, and can you refer the reference, the Anguchem paper reference is also given in the the lecture. So request you to go to that Anguchem paper if you want to read in details. Otherwise, if you can explain that what exactly is not clear to me, we can focus in trying to explain what you did not understand. That would be more better, or refer to the original paper. What we can do is we can give the reference of the paper once again in the online Google. You have a forum, no? Forum, so that you can download the reference yourself. You can just write it down that we will give the reference in the Google forum or whatever. Not upload the data. You cannot upload. Just give the reference. You will have to get it. Once again. You don't have the PPT right now, do you? Okay, so going back to our the discussion on the nature of the catalyst. The active species were metal carbene compounds, which are extremely reactive compounds, and also they are very unstable in the sense that they had metal ligand multiple bonding. And what the catalyst which were used for metathesis reactions are mainly molybdenum, tungsten, tantalum, ruthenium. So what is Professor Grubb's contribution is that he was the one who made the ruthenium catalyst, which later on became famous as Grubb's catalyst, and that catalysts were extremely air and moisture stable. They were functional group tolerant. So the biggest contribution of this catalyst were that they brought this whole of air sensitive chemistry out of glove box to be able to practice in aerobic conditions. You've gotten it, no? So that is what is Professor Grubb's contribution. No, there is a Harman's work. Go down. Okay, that slide. That one. Can you type that? The reference that Sudipta has asked for is Anguchem 1998, volume 37, page 2490. Can you just give this? In the forum. Copy it. Control C. Apple C. So the reference. So we have Navita Kumari. Navita has asked Niva. Sorry, Niva. So Niva has asked a very important question. It says, what are the industrial applications of shop process? Yes, the shop process is a shell higher olefin process. Shop process contains three important organometallic reactions. The first is this alpha olefin, production of alpha olefin from ethylene, or this is alpha olefin oligomers from ethylene using a nickel catalyst, which is what is the shop process. And the second thing is isomerization, where the alpha olefins, which are terminal olefinic bond, get internalized by the isomerization reactions, and the bond appear in the middle of the uh, 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 this beginning of the olefin, middle of the olefin chain. And then third is metathesis. Now the industrial applications for shop process was to be able to use the fraction which was less than C12 fraction, which are very short range oligomers, or very high range alpha olefins which are over C40. So the swap process sort of helped the unwanted fractions less than C12 and higher than C20 to be and then used three combination of reactions to bring them over the useful range, which was between C14, C12 to C18, and then these alpha olefins of this range C12 to C18 can be used to make fatty alcohols, which were at that point in demand for making linear fatty alcohols, which had applications as soft detergents. So the industrial, to answer your question, that industrial scale applications of sub process was catered to the production of soft detergents, which were linear fatty alcohols. And for that they had to come around using three different important organometallic reactions: alpha olefin oligomerization from ethylene, followed by isomerization of olefin, followed by olefin metathesis. These three reactions were put in place as a part of the Schwab process. And there one can see the depth and the scope of organometallic chemistry coming around. Do you have any other questions? Please, to all the viewers, requesting you to send us your queries, and we have heard some very important questions coming around. If you can take a snapshot of these of that graph and just give to the Anglican right now.
Okay.
You can have a screenshot.
This one.
Apple 4, I think. Command 4 gives a screenshot. No, command 4. Just see, not. Please send us your queries. I think go escape from here and now command 4. Escape the program. Now set command 4. No. Shift Apple 4 maybe. Shift command 4. No. Shift option 4. Just see some Google it up how to take a snapshot, screenshot. So please send us your queries. We have received in iMac. Shift command 4, no, not like that. See how to take it. Then no. Option 4. Now just take a look at the key, which key they said. Shift command and 4 together. All three should be together. Maybe the keyboard is different. Please send us your queries. You can help. Can you take a screenshot of this slide? Screenshot. Show him the window. Show him the window that showed. No, the window which explained. Safari window, Google window that showed how to do it. Hmm? Okay, can any other metal? There is another question from Niva Kumari. Can any other metal other than ruthenium become useful for metathesis? Niva, there are many metals. For example, Schrock has developed tungsten, molybdenum. They also do metathesis reactions. Many transition metals, mid-low transition metals, as well as late transition metals, if they have a metal carbene moiety, they would be able to carry out olefin metathesis. It's not only exclusively for ruthenium. However, the why then ruthenium is so special? Ruthenium is very special because ruthenium can do it in presence of air under aerobic conditions. So which other metal, for example, Schrock's metathesis catalyst, molybdenum catalyst, may not be able to do in presence of air. So they need stringent exclusion of air and moisture for them to do the catalysis. So yes, to your comment saying that can other metal? Yes, metal like molybdenum, tungsten, they have been tantalum, they have been reported to do olefin metathesis. However, those reactions are done under stringent conditions like exclusion of air, and in that way ruthenium is very special, as I was mentioning, that it brought the whole air sensitive chemistry out of the glove box, dry box, to be able to practice in open air, and that's why people tend to often use ruthenium. But other metals are equally, many other metals, I named two of them, molybdenum, tungsten, can also do the same. Can you succeed?
So we took the picture, but we're not able to update it here.
Why?
We can't attach anything.
No, this, we go to emoji, there it can, yeah. It will take you to, then add picture, photo. What is, these are all, go down or up and down, there should be some picture option, add picture. This is chat mode. No, these are all emojis. Other than, can you not add picture? What about the keyboard? Keyboard. Okay.
I'm not able to remember.
Okay.
We tried to show directly this slide.
Okay, there will also be ready. Well, please send us your queries. We have had some very important queries. Please send us your queries. Then how do you project it?
This is what they are saying, right? No?
They will say this or what? Not yet, I think. This is one of the windows. You might see
Transition पे click करिए. यही है ना window?
Okay, so Sudipta, this one is for you. So here is this Harman's paper, this Anglican paper. Request you to sort of go through it, where he had shown how the ruthenium carbene complexes were better than the first. Okay, can we just go back?
Transition.
Oh, take it. Okay. Okay. So, do you have any queries? Actually, Grubbs and few other papers are also there who had shown that the second generation or catalyst with NHCs, they perform better than the first generation. So, request you to send us your queries. They're sending. How many people are there?
No, 5.
Okay. So, what is the beauty about organometallic catalyst? The field is that there are many large-scale industrial processes which where the challenges have been met using organometallic chemistry, and that is kind of amazing to see how the metal-mediated reactions or catalysis can take up some of the very daunting challenges and provide solution for large-scale production of these commodities. So that's kind of the beauty of the field, and we had in the beginning seen how this was appreciated with the conferment of 9 Nobel Prizes in a total 110 or 20 year old history of Nobel Prize as such, and that sort of speaks volumes about the strength and the capability of the field. And this course also focuses on these important applications that has come out of organometallic chemistry in terms of benefit to the society at large. And from that context, we have taken up 2 important reactions. First one was the Repi synthesis, followed by olefin metathesis, both of which can be taken to be as a birth child of industry. However, academia too played a vital role in developing these 2 reactions to their fullest extent. So, do you have any questions? Request you to send us your queries. Sudipta, did you see the slide that we put it up again for you to see, to show the Hanuman's work? How long have you been?
Already 29 minutes.
Okay, only 1 or 2 will. You just send the SMS or something. Well, We will be around for another 5 minutes or so, and if we'll wait and we'll try to see answer your queries, and in absence of any we will call it a day. We'll terminate today's live session. So requesting you once again to send us your queries. Another thing towards the end, I should note that alkyne metathesis also draws parallel to alkene metathesis. Their reactions are somewhat similar. Their mechanism, even though fundamentally is conceptually similar, but also differ slightly. So they are not really exactly the same. And the other important thing is that unlike alkene metathesis, which undergoes the active species is a metal carbene species, one can think that for alkyne metathesis the metal carbene species should be metal alkyne species, which is not true. For alkyne metathesis as well, metal carbene species, metal alkene species is carbene species is the active species, and it does this alkyne metathesis in 2 steps, which we have also discussed in details. And the other important difference is that alkyne metathesis is less developed in compared to alkene metathesis. However, to the extent it has been developed, they have a parallel with regard to the alkene metathesis. So we have spoken about alkyne metathesis as well in the lectures that we are covering today in our live session. Well, one last time, please send us your queries if you have any. Otherwise, we are going to conclude today's live session, and we will meet next again in 2 weeks' time. Okay, then if I thank you for being with me, and today we conclude today's NPTEL live session for this course, Transition Metal Organometallics in Catalysis and Biology. I wish you all the best in continuing further with the remaining lectures, and again we will meet in 2 weeks' time. You can send us your queries to the course forum, online forum, during this time, or you can also write to us during the next live session, which will happen in 2 weeks from now. So till then, goodbye and thank you.